And don't worry if I'm recording or whatever, you're more than welcome to still chime in and ask questions and answer questions. So if we take a look here, Friday, January 8th, where we made it, felt like 2 weeks instead of 1 week, but we're going to go over Boyle's Law. We're going to work through the lesson, Charles' Law and Gay-Lussac's Law. Again, that's the end of this lesson right here. Don't forget Monday is an asynchronous day. So if we take a look, week 2, I should say week 2. I will not be meeting with you. There is no Zoom, no in-class Zoom. You were to work through page 7 and 8 of the packet over combined gas law, which is basically the notes that we are going over today and that lesson that you just saw on Friday. Tuesday of next week, we'll review combined gas law and we will have a combined gas law homework quiz. Wednesday, another Mythbusters over what's called water heater rocket. Thursday, in class, discuss the Mythbusters, Dalton's law of partial pressure, work through partial pressure problems, and then we'll do a pre-lab for the combined gas law. All the laboratories in here in this class I've recorded. So Friday, you'll be able to just go to the laboratory link and play through that and fill out the laboratory sheet as the video plays. Again, on this Friday, I will be here if you need help. On this Wednesday during the Mythbusters, I will be here during class if you need help. Unfortunately, on Monday, I will be in meetings all day on Monday. So keep that in mind. Last but not least, let's go ahead and get on discussing kinetic theories. So open up your packet to page 3 is where we left off. Just to make sure that you guys understand, Google has given you guys these great Google books, Google Chromebooks. I was lucky enough to purchase one also for myself, just so I could show you guys how to use it. Now, a lot of your teachers don't have these, so they have no clue of the capabilities that you have. If you were in my class last semester, we went all through those. Maybe I'll post that video up again, but maybe there's some misconfusion of how you're to turn in assignments here. So you have what's called a stylus. If you reach under the laptop, there should be near the front right, a little thing that you can pull out. And I actually use this laptop to grade things. Just so you have the idea, I'm using it too, very similar to how you guys are using it. If you take a look, I've got 30 Mythbusters here that are to be graded. So just so you know, that Mythbuster assignment right here is the way that it should look whenever you go to it. If you've not done it yet, you should click on to this. And then hopefully you have like YouTube on a TV or something like that. If you don't, you can actually open up 2 windows and basically do like a split screen. Let me see if I remember how to do that. It's been a while. Let's see if I can. Open in a new window. Let's see. I'll go ahead and pause it real quick. But
now from high diving, those bracelets, just like this, right? Sure.
Maybe. There we go. So we should be able to. And does anybody remember from last semester? I was able to do it quite well. Nobody remembers? Oh, there we go. Well, anyway, you can switch between the two, but what you want to do is you want to make sure that you get this file here. And it's in the download manager down here. I'm going to go ahead and switch this to this way. That's probably the way you have to do it. But we go to show in folder. And then I click on that Mythbuster. One of the first things I may want to do is go ahead and change that name. And you can do that by basically going here. Oh, not there, but showing in the folder. If you do this, you can actually click right on it. Oh, dang it, it's been so long. Where is that showing folder? How many of these have I downloaded now? It's in my drive, and we can, I think I just sent it somewhere else, but you should be able to basically get in here and type, and it may be because I'm in a different mode right now. But basically, once you get this thing on, you can come up to here, and at the top, you see this little pin. If you click onto that, then you will be able to basically draw right on this. So you can put your name. And there's a terrible, whatever you call it on there, glare or whatever. What's the title of this one? Big Squeeze. If you don't like how thick you're writing or whatever, if you want to write a little bit thicker, you can change that. It's actually kind of better to write a little bit thicker on here. But even my terrible handwriting, you can see if I take my time with it, it is a little bit, you know, it's decent enough to see. And the more you zoom in, describe the actual myth, you know, a diver helmet could implode or collapse if loss of pressure inside. So if you zoom in and then whenever it zooms out, it actually looks a lot nicer than it would if you had it here and you were trying to draw. So if you have normally bad handwriting, the more you zoom in, whenever I get it or whenever you look at it later, it'll actually look nicer whenever you zoom out. So that's some things for you. And then basically you save this file, and this is actually the file that you submit to me. And if you're in this mode, that's how you do it. I just remembered you've got to have it folded like this, and then you basically drag one of the windows over to the side. So you could have this playing here.
Pressurizer using a compressor on a boat at the surface to counteract the external water pressure.
While you fill it out
Well,
over
that sounds
here.
like an accident waiting to happen, and that's what this myth is about. If that compressor were to stop, or the air hose were to get cut.
So if you don't have multiple devices, that makes it nice. And if you want, you can actually, like, once you get that set up or whatever, then you can fold it back, unfold it back out. That's all we've got. Questions? So then whenever you do come back here, you would go to, I think there's a little submit button down here at the bottom. You click that, you find that file that you saved with all the work on it, and then you submit it. As you can see, a lot of you have already submitted that. 0 out of 30 are graded. I'll probably grade that this weekend. If you are not one of these 30, please make sure you get that into me. Please make sure you get it into me. Questions about using this? I assumed that a lot of your other teachers had used these things in the past. I think that is the easiest way to do it. Some of you guys use other things and it looks like you've typed and stuff in there. That's fine. One thing I do want to check real quick through here. Some of you guys, yeah, document cameras look nice. Definitely fine. One thing I do want to show you guys here, and can I actually, I don't know if I can. So if we take a look this is very common, is that somebody turns in one that is completely blank. So they think they've turned in the file, but this is just a blank one. I cannot grade that. So you might want to check to make sure that you've turned it in. I cannot grade blank ones. This is another problem that some people are experiencing, and I had you last semester, so I'm comfortable. Like Kennedy, remember the ending of this should be .jpg. If you do this, then a lot of times it won't actually download, and I won't be able to see it and actually write on it to put a grade on there. Looks like yours came up okay though. Just remember to try to put .jp or .pdf works too. But yeah, looks like a lot of people were able to get this pretty good. Cool. It looks like the other teachers were on par with doing it. Oh, don't lose this guy either. Your little stylus is so sad. All right, without further ado, yesterday we talked about Boyle's law. We said that if you decrease the volume, the pressure goes up. If you increase the volume, the pressure goes down. Easy enough. Today we want to talk about Charles's law. So if I take this balloon and I put it in a freezer, or in this case it says, what if I take this and I put it in the oven? Does the number of particles change in here? I will turn on the chat, which you guys are so quiet in the morning. Number of particles does not change in here. The only way the number of particles can change is if I open this up. Very good. So particles stay constant. If I put this in a hot room, the particles, well, what does change immediately? We know that the temperature changes because the balloon is in the hot room now. So that's going to increase. What that means is the particles will move faster. Initially, that will cause the balloon to get bigger. Some people say that when we heat things up, they expand. Well, the balloon would expand when we heat it up because the particles are moving faster, which means they're hitting the wall more often until they get a consistent volume. The pressure inside the hot room, well, it's still going to be atmospheric pressure. So there is no change in the pressure. The reason for that is if the container could not change, like the balloon could not get bigger, then the particles moving faster would hit the wall more often and it would increase the pressure. But the fact that the balloon can expand means it will expand until the pressure inside is equal to the pressure outside again. So that's the key. The fact that this is stretchy material and the volume can change means that the pressure will stay the same. And we know that too from yesterday. I had that syringe. If we were to heat up this syringe, this would slowly move out. But keep in mind that the pressure would always be consistent on this plunger. So as this heats up, it would equalize the pressure. We know that there's no change in the pressure. Otherwise, this would continue moving constantly. Same thing with the balloon. We know that the pressure is consistent here because it's not constantly changing shape and size. So what this means is that these are directly proportional. As one goes up, as temperature goes up, volume goes up. If temperature goes down, volume would go down. If you are fortunate to have like a balloon or rubber band, check this out. If I put it on like the part above my lip, where my skin is a little bit sensitive, and I stretch it out, I increase its volume, I will feel it get hot. Now, if I take it away from my lip, you can do this with the rubber band too. I take it away from my lip and I have it stretched out already. And I put it on there and I bring it in, it gets very cold. So the decrease in volume makes it chill as well. That's how your refrigerator works. It works by a pump. It changes the volume to change the temperature. So this is a representation of Charles's law. Again, initial volume divided by initial temperature equals final volume divided by final temperature. And when I was a kid, there was this kid named Tommy Palmer. Tommy Palmer was kind of like, if you've ever watched a show about kids whenever they're in elementary, middle school, that was Tommy Palmer. Tommy Palmer had like long hair, but it was only long like in one part. We called it a rat tail back then. So it wasn't like he had long hair like a ponytail. He had kind of weird long hair, and then like coming down from the back of his hair was like, I don't know, maybe 100 strands of hair, known as a rat tail. You can look that up. But he was kind of a bully. We didn't have internet. I'm sure that he's probably on Facebook bullying people today. I don't know if he ever got over it all. But Tommy Palmer, we were at a party once, and we had like everybody was going to camp out, and we had tents and everything, and we had a little bonfire. This was probably about 6th or 7th grade, and Tommy threw it wasn't a Coke, but it was like a Big K cola or something like that. He threw that into the fire, and he said, "Watch this, Jackson. Watch this, Jackson. Watch this." And within about 30, 40 seconds, that can exploded because the soda inside started to vaporize, and it had to go somewhere. And as it did, it popped that can. A girl named Stacy Neal, she was sitting close to the fire, and the hot soda actually gave her like a scar on her. I think she even had it like all the way up, like, well, as long as I remember, like senior year, she had this like cola scar. It just basically burnt her skin. Thank you, Tommy Palmer, right? But yeah. So what happens if I put a Coke into something hot? Well, the number of particles, again, does not change because that can has a set number of particles. The volume, well, the can itself is very rigid. Rigid can, rigid means it doesn't change until it explodes. Temperature, we know Coke in a fire, in an oven, the temperature will increase. That makes the particles move faster. The particles move faster. They're colliding with the wall of this Coke container more often. If they start colliding with that container so much that it breaks down the integrity of the container ruptures. We know that if we keep blowing up a balloon, the pressure in there gets so big, the container's integrity fails, it ruptures. As temperature goes up, pressure goes up. This is Gay-Lussac's law. These are directly proportional. So notice all of the changes that we've done have a set number of particles. The particles never change. It's only the temperature, pressure, and volume that can change. Keep in mind, you may have heard that heat rises. In reality, as you increase the temperature of a gas, the the particles spread out more. So they become higher volume, even though they're the same mass, which means that they become less dense. So heat does not rise. The actual heated material is less dense, and therefore it rises. A lot of people say hot air rises. That's true. The hot air will actually rise. It's not the heat, it's the hot air that rises. So scientists then take PV equals P1V1 equals P2V2 and add that to either P over T or V over T equals P over T or V over T into one big law known as the combined gas law. So in science, you'll find that we need to do a lot of reaction rearrangements. So if we take a look here, I'm going to rearrange this formula to solve for P1. So what I need to do is I need to multiply both sides by V1. So that's going to put V1 on the bottom of the other side. And then I want to get rid of T1 as well. So I'm going to multiply both sides by T1. And basically that would be our new equation. Or let's say I wanted to solve for V1. And I think that's what we're going to do here. A sample of gas occupies 150 milliliters at 25 degrees Celsius. What is its volume when the temperature is increased to 50 degrees Celsius? So a lot of times the nice thing would be to make a nice graph here. We know that the number of particles is not going to change for us because we've not discussed that formula yet. So that's not applicable, or you could just say equal, equal, equal. The initial volume of the gas is 150 milliliters at 25 degrees Celsius. Remember what we said about temperature for this. We can never use degrees Celsius in a formula. We need to change that to Kelvin. 25 plus 273.
It's 298.
That's 298 Kelvin. So the initial temperature of the substance is 298 Kelvin. What is its volume when the temperature is increased to 50 degrees Celsius? 50 plus 273.
The answer is 323.
323 Kelvin. I want to find what the new volume is. So that right there is what I want. Now, as I said particles for this. In actually means particles. Luckily for me, the pressure is also constant. So we don't need to worry about these. So in our formula, we can actually ignore that. V1 over T1 equals V2 over T2. Now, we can conceptually look at the 298 Kelvin goes up to 323 Kelvin. It increases. That's the effect. Well, if we recall, if the temperature goes up, the volume should go up. So the effect here should go up. That means that whatever I find out for the final volume of this, it should be greater than 150. So let's solve for V2. That means we're going to multiply both sides by T2, and it's going to cancel out right there. So then I can substitute in 323 Kelvin times 150 milliliters divided by T1, which is 298 Kelvin. If it's on top, we multiply. If it's on bottom, we divide. Kelvins will cancel out. 323 times 150 divided by 298.
It's about 162.5838.
163 milliliters. Is that greater than 150 milliliters? Yes. So that is correct. Questions there? 2, the pressure in a bicycle tire is 105 psi at 25 degrees Celsius in Fresno. You take your bicycle up to Huntington, where the temperature is -5. What is the pressure? So volume, these bicycle tires have the same volume, and they're going to have the same number of particles. So we don't have to worry about those two things. We have P1 over T1 equals P2 over T2. We are looking for P2. The initial pressure is 105 psi. The initial temperature is 25 degrees Celsius, but we cannot use that. So we're going to replace that with 298 Kelvin. The final temperature is -5. -5 plus 273.
It's 273.
-5 plus 273.
The answer is 268.
268 Kelvin. So what happened to the temperature as time went on? It went down. So if the temperature decreases, what should happen to the pressure? Oh, here we go. If the temperature decreases, the pressure should go down. So we're assuming that's going to go down. Let's take a look. We're solving for P2, so we need to multiply both sides by T2. It cancels out here. So the temperature 2 is 268 Kelvin. The pressure 1 is 105 pounds per square inch. The temperature 1 is 298 Kelvin. Kelvin will cancel out. 268 times 105 divided by 298.
It's about 94.4295.
94.4 psi. We predicted that if the temperature goes down, the particles will not collide with the walls of the tires as much, so the pressure should go down. Remember, I always need to make sure my temperatures are in Kelvin, because that's an absolute scale. If we would have done this with -5 and 25, we would have gotten a negative pressure. You cannot have a negative pressure. What would be the new pressure if 250 centimeters cubed of a gas at standard pressure is compressed to a volume of 150 centimeters cubed? With this one, both temperature and number of particles is constant. So we have P1 V1 equals P2 V2 from our original equation, because the temperatures will be the same. So it will cancel out. We know that we have 250 centimeters cubed. We know it goes down to 150 centimeters cubed. As volume goes down, pressure should go up. As volume goes down, we put the squeeze on it. So the pressure, the particles should be hitting more often. It should go up. It says, what would be the new pressure if 250 centimeters of gas at standard pressure is compressed to that volume? Well, we talked about standard pressure early on. We said that standard temperature and pressure, standard pressure is 1 atmosphere. We could use any one of these numbers we wanted to, but that would determine our unit of pressure. Let's see if they ask for a particular unit of pressure. They do not. So the easiest one for me to do would be 1 atmosphere, because it's the number 1. Pretty easy. So if we want to solve for pressure 2, we need to divide both sides by volume 2. It cancels out right there. So pressure 2 equals 1 atmosphere times 250 centimeters cubed divided by 150 centimeters cubed. Notice centimeters cubed will cancel. 1 times 250 divided by 150.
That would be about 1.6666.
So 1.67 atmospheres. We said that if the volume goes down, the pressure should go up, and that's exactly what we're seeing there. Last one, it looks like we've got all three. We've got volume, temperature, and pressure. So PV over T equals PV over T. So we know that the number of particles is constant because it's not changing. What would be the new volume if 250 centimeters cubed of gas at 25 degrees Celsius, which we convert to 298 Kelvin, and 730 millimeters of mercury. We know that all of these are the same ones because of words like at and. So all of these go together. It's this, at this, and this. We're changed to standard conditions. Well, STP equals 273 Kelvin, and for millimeters of mercury, it's 760 millimeters of mercury. This one's a little harder because the temperature goes down, which we would assume makes the volume go down. Oh, it's okay. The pressure goes up, which you also assume makes the volume go down. So it's likely that the volume of this will be lower. We are looking for V2. So we need to, your teacher might have taught you to cross multiply or whatnot. So we get the T2 up there and we get the P2 down here. Now it's just a matter of plugging this in. And you need to keep track of everything here. The finals are the 2s. So 273 Kelvin. P1 is 730 millimeters of mercury. V1 is 250 centimeters cubed. All of this over P2, which is 760 millimeters of mercury. And T1, which is 298 Kelvin. Notice Kelvin and millimeters of mercury will cancel out, leaving us with the unit for volume. If it's on top, we multiply. If it's on bottom, we divide. 273 times 730 times 250 divided by 298 divided by 760.
It's about 219.9863.
219, actually about 220 centimeters cubed. And as I said, as temperature goes down, we expect the volume to go down. And as the pressure goes up, we expect the volume to go down as well. It's 220 centimeters cubed. That's how you use the combined gas law. For Monday, and you're more than welcome to do this over the weekend. That way you don't have to get up this early on Monday. But for Monday, you are to do page 7 and 8. Let's take a look at that. So if we take a look at Monday of next week, remember there's no Zoom. You were to work through page 7 and 8 in the packet. That is the combined gas law. You're working on that for the combined gas law quiz on Tuesday and Wednesday. The combined gas law quiz is 5 questions, pretty short. So basically, you'll be able to read through here and determine how you're going to rearrange this equation and what you need to do. So it says a gas occupies a 36 liter. There's a volume. Let's just call that volume 1 at 29 degrees Celsius. 29 plus 273.
The answer is 302.
There's our temperature. And 2.1 atmospheres, that's our pressure. Assuming the volume cannot change. So this is also our volume 2. what temperature, that's what we're looking for, is needed to give a pressure of 4.94 atmospheres. So we have P1 over T1 equals P2 over T2. We don't need to add volume. We can, but it's not going to change. So that's going to cancel out. We are trying to solve for temperature. So your math teachers have hopefully taught you to cross multiply. And we get T2 times P1 equals P2 times T1. We then need to isolate T2. So we're going to divide both sides by P1. That will cancel it out on that side. So T2 equals P2 T1 over P1. Now it's just a matter of plugging in these numbers into the equation. Remember, this is chemistry, and this is mostly what you do in chemistry. You rearrange formulas and you plug things in. 302 Kelvin. And then we want P1 on the bottom, which is 2.10 atmospheres. Atmospheres will cancel out, leaving us with Kelvin. 4.94 times 302 divided by 2.10.
It's about 710.419.
It gives us 710 Kelvin, 0.4 Kelvin. But the problem is that they want this in Celsius. Well, that means we need to change from Kelvin to Celsius. That's not a problem. We just need to subtract 273. 710.4 minus 273.
That would be 437.4.
So that becomes 437 with 3 significant digits, 437 degrees Celsius. You were to continue with problems 2, 3, 4, and then on the back, there's a little graphing exercise that shows you what happens whenever you compare temperature to volume. And then 6, 7, and well, I'll just change this to 8. These are math problems again, and this is a conceptual problem. That's the assignment that is due Monday. Don't forget, I will not be in the Zoom Monday. We have meetings all day. If you've got questions, by all means, stick around. We've got about 10 more minutes. Otherwise, have a great weekend. This Zoom will be up. So if you need to go back through anything and recheck anything, by all means,